Why the means it is too hot out here. But anyway, I believe that God will show some mercy and there will be better time, but it's too hot. Okay, so if I have a 3D surface, then or if I have any equation, either it is kind of either it is kind of a 2D or a 3D. Okay, like if I have a 2D kind of surface. Okay, so I have equation like y equal to uh, w- y equal to x cube. Okay, so y equal to x cube. So this is a line equation. I mean it's a 2D. So x and y they both stay on a plane. So if that is true, then y equal to x cube is the 2D equation. Now, can we deduce a tangent at any point? So that is a concept. What we want. So we want a tangent at any point. So a point is alpha because it's a single dimension. So only x equal to something that we want. So y equal to fx and y equal to fx equal to x cube. So if I want tangent at any point x equal to alpha, the equation of tangent that passes through origin would be y equal to mx. This is what we have been seeing. Y equal to mx, where m is dy by dx, differentiation at point x equal to alpha. So if it is x cube, then it comes to a 3x square, 3x square. So the tangent at point tangent changes over point to point. So equation of the tangent at point x equal to alpha is y equal to mx, y equal to 3 alpha square x, y equal to mx where m is dy by dx, differentiation at x equal to alpha. Then y equal to mx is the equation of the tangent at point x equal to alpha. Then it comes to y equal to 3 alpha square x. So this y equal to 3 alpha square x is equation of a line that is tangent on a curved line on a polynomial line y equal to x cube at point x equal to alpha. So this is what we know. Okay, what is what is normal vector at tangent? What is gradient vector? What is normal vector? What is tangent vector? So repeatedly I have shown that if you consider the vector as a line, if you consider vector as a displacement, then probably it is difficult to understand. But if you consider vector as an energy source that has a direction and it has a magnitude, so if that is the case, then if energy is moving in a certain direction and if you are standing on x-axis, y-axis or z-axis, then how much you would get the energy essence. If you understand this concept, then things are pretty much easy. Means any complex thing is nothing but it's a step by simple thing. If simple thing, if you do step by step, then any very big thing you can achieve. So if you have an energy source that is moving in a direction, and if a person is standing on three component x, y, z axis, how much energy he is feeling. So if he understands that, then he can deduce the components and everything. Now, if there is a curve like this, if this is x-axis and this is y-axis and x is like this, then at any point alpha, what would be the equation of tangent? Considering that it is a vector, means it is passing through origin. Then y equal to mx is equation of any linear line passing through origin. Or if it is passing through y0, x0, y0, then y minus y0 equal to m, x minus x0. So where m is the slope of the line. So slope at any point, if this is the line curve, slope if I consider tangent at any point, whatever is the slope, is dy by dx. If it is x square, then 3 alpha square. If that is the case, then 3 alpha square x mx y equal to 3 alpha square x is the equation of the tangent at that point. If that is true, then what is the gradient? So we understood that if we have the tangent equation, then we can calculate the gradient. So now if I take it as gradient, then it will come as 3x square. Gradient is nothing but dy by dx I. So 3x square is the gradient. Okay. What is the direction of the gradient? So gradient direction generally that is found is perpendicular to the tangent. Okay, I think I can demonstrate it more. So now question comes is, if I know how to calculate the tangential surface, then how we can calculate normal at that point? So that is a question. Now let's go to the our kind of whatever we have demonstrated so broadly, that is three dimensions. Now I have a surface. On this surface, I have x. Okay, so I have x and I have y. I have x and I have y. If this is xy, then this is xy plane. If this is xy plane, then fxy is any function over x and y. If that is true, then z equal to fxy. If that is true, then on this surface at any xy plane, we have vertical z values. Okay, so if I take x, y, any location, then I have vertical z value. If that is true, then if I take like equation like 1 minus x square minus y square, a square root, if I take out the square root also, it's a kind of a sphere equation. So z equal to 1 minus x square minus y square root. This is equation of a sphere. Means at each x and y, if I calculate the z and if I keep calculating it all over the xy plane, it will result in a height, varying height. Okay, if this is xy plane, then z value will vary at each xy depending upon the 1 minus x square minus y square root. If that is true, then it will lead to a sphere. Okay, so if I say dz by dx, that is partial derivative, then for a delta x variation along x axis, how much z changes? So dz by dx, how much z, how much z changes if there is a unit change along x axis? Okay, and how much y changes dz by dy if there is a unit, if there is a unit change along y-axis, so that will come in an equation. How much j changes along any vector u if there is a unit change along that vector? So that is dz by du that we calculated. Now we come to a kind of equation. So we have one equation, that is surface equation, that is z equal to fxy. So z is equal to 1 minus x square minus y square root. Okay, so this is a surface equation that anyway we are getting. What about what we have seen, that if we want to calculate directional derivative like dz by du, variation seen in vertical direction, that is z, per unit change in any vector u. So dz by du, there are two things. One is that we want to, if this is u, this is x vector, this is y vector, this is any vector u, then at any point gamma, or we can say in xy a comma b, at any point gamma, what is the dz by du? If that is true, then we have to calculate the z at gamma plus delta u, and we have to calculate z at gamma. If we know both z, then delta z we have to calculate, and delta u anyway we get. So delta z by delta u is nothing but dz by du. Now at any point a comma b, we can calculate the delta u, as since a and b are xy. So f a plus delta ux, delta u's component on x axis, and f a plus delta ux comma b plus delta uy minus f a comma y divided by delta u. So whatever delta u we have taken. So that is dz by du. So this is one way of calculating, but since it does not give the formula, we went to local linearization. Local linearity is nothing but at any point on the surface. So if we have a surface, then at any point on the surface, what is the equation of the tangent? So if I have fxy, so if I take any point in the xy plane, if any point on the xy plane, then for that point we have a z value. Now, fxy equal to some equation. So, if you want the tangent, like we calculated y equal to x cube, if you want tangent equation of the tangential line, that is linear equation, then y equal to mx, that is y equal to dy by dx at a point where we want to calculate the tangent. So dy by dx, that is 3x square, so y equal to 3 alpha square x. The equation of the tangent at any point y equal to x cube when we are calculating tangent at the point x equal to alpha. Like that, if we want tangent at any point a comma b in 3D, then we have to calculate m1x plus m2y. So z equal to m1x plus m2y. If I calculate this, then m1 is nothing but dz by dx and m2 is nothing but dz by dy. So z equal to dz by, so now we are calculating the equation of tangent surface. Okay. So if I have in xy plane, if I have if I have a line called u, so in xy plane, if I have a vector called u, so on this vector u there is a point called a comma b. If a comma b is a point on any vector u, then if I want to calculate, so if fxy is z, then fab would be some z value. So if fab, so if this is a surface, suppose it is a sphere, and this is xy plane at AB point, there is a z value, so that is a surface. There, if we want to calculate the local linearity at that point, you can visit our other videos for local linearity. So local linearity is nothing but if someone zooms in a 3D graph, then at particular point, okay, what is the linear surface equation if it is 3D? So that is nothing but same as 2D what we calculate y equal to mx. Here it is z equal to m1x plus m2y. Now m1 is dz by dx and m2 is dz by dy. If we are calculating at point A and B, then it is dz by dx where x we have to substitute with A and dz by dy there y we have to substitute with B. If that is the case, then we get an equation of tangential surface. Now we get z equal to dz by dx at point A x plus dz by dy at point B y. Nice. Now we have z equal to m1 x plus m2y. So this is a 3D equation in a sense that for varying x and y. Okay, so varying x and y, what is the z value? Now, can we, so if I get this tangential surface, then what is delta z? So z equal to m1 x plus m2 y, then delta z is m1 delta x plus m2 delta y. Because if I take z at another location, that is a plus delta ux and b plus delta uy, and then if we subtract, then we get the delta z. So delta z is nothing but m1 delta x. So delta x is ux, delta ux. So if I have a xy plane and in the xy plane I have any vector u, on the any vector u I have taken a kind of a cut of delta u, then I want to calculate the difference derivative of fxy along unit vector u. If that is the case, then for any cut of delta u, there is a component on x-axis at delta ux and component along y-axis is delta uy. If that is the case, then if I calculate the local linearity, at point A comma B, where we want to calculate the directional derivative, then it will come as z equal to m1 x plus m2 y, where m1 is dy by dx, dz by dx at point A, and m2 is dz by dy at point B. Now, what about at point A plus delta ux and B, point A plus delta ux and B plus delta uy? So, if I subtract both, means z at AB and z at A plus delta ux and delta B plus delta A, z at point A and B, and z at point A plus delta ux and B plus delta uy. If that is the case, if I subtract, I get delta z. If I get delta z, that is nothing but dy by dx at point A, delta ux plus dz by dy at point B, delta uy. So I repeat it. So if we want to calculate dz along any line, if I have a line called u vector, along v vector, if I have taken a delta u unit of distance against delta u or unit of distance, there are 2 points. One point is a dot v, another point is a dot v plus delta u. So that will nothing but a plus delta ux comma b plus delta uy if we take the components. If that is the case, then delta z as per the local linearity equation, that is separate thing. As per the local linearity, z equal to m1x plus m2y. So delta z would come as delta z means a z difference in z at 2 points a dot b and a plus delta ux, b plus delta uy would come as delta z equal to m1 at a, delta ux plus m2 at b, delta uy. Z equal to m1 at point at x equal to a into delta ux plus dz by dy, dz by dx at a into delta ux plus dz by dy, delta dz by dy at y equal to b into delta uy. So that is the equation of the tangent. So now can we do some shifting? Delta z equal to m1 delta ux plus m2 delta uy. I can take delta z on right side and I can equate it to 0. So m1 delta ux plus m2 delta uy minus delta z equal to 0. Okay, so I think I can make it even, I believe, little simpler. So for the tangential equation, the actual equation is z equal to m1x plus m2y. Now I can take z on that side, then it will come as m1x plus m2y minus z equal to 0. I am not taking any interception. If I take interception on the axis, then it will come as or even I make it more simpler, then it will come as m1 x minus x0 plus m2 y minus y0 plus m3 z minus z0 equal to 0. Okay, if I don't take m3, then m1 x minus x0 plus m2 y minus y0 minus z0 equal to 0. If I don't take negative and make it positive, then it will come as m1 x minus x0 plus m2 y minus y0 plus z minus z0 equal to 0. Now, if I take the m3 component, that is crucial. So, m1 x minus x0 plus m2 y minus y0 plus m3 z minus z0 equal to 0. This is the generic equation of tangential surface. If I take x, y, z all along, okay, so if whatever is coming, we considering it is there is no interception, means its origin we are taking, then m1x plus m2y plus m3z equal to 0. If that is the case, then m1 is partial derivative along x-axis, that is dz, that is whatever the equation, whatever equation we have actually. So like if I say z equal to 1 minus x square minus y square is the equation of the surface. So that leads to 1 minus x square, z square equal to 1 minus x square minus y square. So 1 minus x square minus y square minus z square equal to 0. If I take the equation of surface, then x square plus y square plus z square equal to 1. This is the equation of a surface. But if I take as a function, then it would come as fxy equal to 1 minus x square minus y square to the square root. But if I take fxy as z and do the all mixing, it will come as 1 x square plus y square plus z square equal to 1. This is equation of the surface. Okay, if I take z into the account, then what about the tangent at any point ABC? That will come as dy by dx, x plus dy by d, whatever the function we have. So if I have a function in xyz, so fxyz. Okay, so partial derivation of fxyz with respect to x into x plus partial derivation of fxyz with respect to y into y plus partial derivation of fxyz with respect to z into z equal to 0. I repeat it again. So if I have a surface as fxy, that is 1 minus x square minus y square to the square root. So since fxy we call it z, so z equal to 1 minus x square minus y square to the square root. That will come as z square equal to 1 minus x square minus y square. That will come as 1 equal to x square plus y square plus z square. So now if I take everything on, so I can also call it x square plus y square plus z square equal to 1. So I have another kind of equation that is in term of fxyz. Earlier we had in term of fxy. Now I have in the term of fxyz. fxyz equal to 1. So fxyz is nothing but x square plus y square plus z square. If I put at any value, that will become 1. Now if that is the case, then the equation of the tangent at any point A, B, C is fxyz into dfxyz by dx into x plus dfxyz by dy into y plus dfxyz by dz into z. That is the equation of the tangential surface. If that is true, then can we see something? fxyz by dx, fxyz by dy, and fxyz by dz. This is another vector dot xyz. This is what we saw in the directional derivative along u vector. If we calculate the directional derivative along u vector, then we got something like this. This is called gradient vector. F dfxyz by dx, dfxyz by dy, dfxyz by dz is gradient vector. This vector dot any another vector, if we do the dot, it becomes the tangential surface. This is what we are saying. Okay, provided that another vector what we are taking, that should fall on the tangent. If that is true, then gradient vector dot that another vector equal to 0. Okay, so now I have a surface equation called fxy. fxy equal to z. So z equal to 1 minus x square minus y square is the surface equation. So z square equal to 1 minus x square minus y square. So it will lead to 0 equal to 1 minus x square minus y square minus z square. So we can say that I have now an equation that is a function of x, y, z. So fxyz is a function that is in term of x square plus y square plus z square equal to 1. This means that any point x, y, z, if I take and if I substitute the value, it will come as 1. If that is true, then I have equation that is variable in terms of three independent variables x, y, z, that is f, x, y, z. If that is true, then at any point A, B, C, if you want to calculate tangent or local linearity, it will come as dfxyz by dx into x plus dfxyz by dy into y plus dfxyz by dz into z equal to 0. If that is true, then dfx by dfxyz dfxyz by dz dfxyz by dy dfxyz by dz, that comes as a separate vector dot x, y, z, x, I, y, j, and z, k. If that is true, then if dot of two, two vectors, so one is gradient vector, one is another vector, that vector is along the surface of the tangent. If dot product of two vectors is 0, means they are normal to each other. Okay, so we calculated the gradient, we calculated the equation like what is the differentiate, what is derivative of a 3D surface along a unit vector u. So u was what we example we taken, it was on xy plane. So derivative of a vector, a derivative of a surface along any vector, that is variation of a surface along any vector, that we calculated, that is gradient vector dot u. So gradient vector dot u vector is the dz by du. This is what we calculated. If we have gradient vector dot u will be unit vector. Okay, so if u is not unit vector, then we have to divide by its magnitude. So gradient vector dot unit vector of any vector, if we do dots, then it gives the dz by du. Okay, but if these gradient vector dot any vector u is 0, gradient vector dot gradient vector means m1, that is dfxyz by dx, that is the m1, dfx dfxyz by dy is m2, and dfxyz by dz, that is m3. So gradient vector dot any other vector, if it is equal to 0, this proves that gradient vector and the u vector, they are orthogonal to each other. If that is the way, then it is only possible because gradient vector is tied to the tangential surface. Tangential surface equation is m1x plus m2y plus m3j equal to 0. If that is the case, then gradient vector, gradient component in tangential equation where m1x plus m2y plus m3z equal to 0, the gradient vector component is there and there is another vector component is there. If another vector component is u and u is in direction of the tangential surface, then it is 0. If that is the case, this proves that the gradient vector is perpendicular to the surface. It is a very, very big thing. So if we calculate the local linearity of any surface, then we get tangential surface. Okay. Now, if we calculate derivative of a surface along any vector u, earlier vector was on xy plane, now u is 3D. Okay, so gradient, now we are calculating the surface, the 3D surface derivative of the 3D surface along any vector u. If we are calculating this, then it comes as gradient vector dot u. This is what we have calculated. Gradient vector dot u. Gradient vector dot any vector that becomes 0 is nothing but tangential surface. If that is true, and gradient vector dot u is derivative of a 3D surface along any vector u, if this also comes as 0, then we are on the same equation at calculating the tangential surface. If that is true, then any vector along we are calculating the gradient vector, calculating the directional derivative, the any vector what we are talking about, that is nothing but that falls upon the on the tangential surface. If that is true, then gradient vector is perpendicular to the tangential surface. Okay, so the idea of the discussion is, first thing that a person should understand what is the concept of the components. Here and there probably we will discuss more about the components, and like in OpenGL 3D graphics where components makes a huge sense, because we have two way of calculating the coordinate system. One is local coordinate system, one is grand coordinate system. So local coordinate system and grand coordinate system, the way we do the matrix multiplication are opposite to each other. So there also we keep calculating components, and then finally we lead to final x y z, because there also it is x y z only. But anyway, now the concept is, if we understand x-axis, if we understand y-axis, if we understand z-axis, then any vector u is the energy moving in a particular direction u, then how much energy someone would feeling if he is standing on x-axis, or if he is standing on y-axis, or if he is standing on z-axis. If we understand these components, then we will understand that if there is a surface, like we gave the example of a sphere, then the gradient vector along then we calculated that we have local linearity. Through local linearity also we have another formula of x, y, z. If that is the case, then through that formula we saw that it is a component of two things, gradient vector and another vector. If another vector, we are thinking that it is the u vector along which we are trying to calculate the directional derivative, then u has to be on the tangential surface to make it 0. If that is the case, then gradient vector what we are calculating, it is the normal to the surface. So if this is, if 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 this is the surface, then at any point this is the tangential surface. At any point, then this is the direction of gradient vector, normal to the surface. So here this is the tangential surface. If this is the tangential surface, then this is the direction of gradient vector, perpendicular. Okay. Now, if that is true, if this is the tangential surface at this location, then this is the direction of gradient vector, because gradient vector dot u vector is 0. If that is true, then u vector is on tangential surface. If that is true, then it is perpendicular to the tangential surface. Okay, so this is the way we find out that what is the concept behind the gradient vector and how it is laid out.